So, I'm Daniel Golovin. I'm going to tell you a little bit about Google Vizier. This is joint work with my esteemed colleagues, Ben Solnick, Shabodip Moitra, Greg Kochanski, John Caro, and Dee Scully. Okay, let me tell you a little bit about BlackBox optimization. So in BlackBox optimization, you have some kind of system, and there's some parameters involved that you can tweak. Think of these as like knobs you can turn. And then you really want to find the best setting of these knobs, right, to optimize some measure of performance or goodness of the system. The problem is that the only way you can find out how good any particular setting of the knobs is to run some kind of expensive experiment or trial, right? And because these things are expensive in some way, in terms of money, in terms of time, in terms of some other resource that you don't have very much of, you only have a very small budget for evaluations of different trials. So this depends on the application, but in some applications you may only have dozens of evaluations. In others you may have hundreds to thousands. Some applications you might be talking about tens of thousands or maybe a few hundred thousands. But we're really kind of interested in this small kind of budget case. And we make kind of minimal assumptions about the objective function that you're trying to optimize here. So in particular, we're not assuming that it's convex or concave. It can have lots of local optima, right, that you really want to sort of avoid. And you're really looking to try to find the global optimum, or at least do as well as you can, given your very limited budget for evaluations. Now, because we make such minimal assumptions about the objective function, BlackBox optimization is widely applicable to many different application domains. So here are a few that we might consider within Google or Alphabet, but there are several others. So one is for things like automated optimization for user interfaces or user experience, or kind of A/B testing for websites. If you have kind of parameterization of some serving system or for some aspect of the website or user experience, you can think of this as like different kinds of website layouts, different kinds of thumbnail sizes, different kinds of color schemes, and so on. You can actually try to optimize those and run an experiment and measure some notion of user response to see which one of these is best according to your chosen metric. Another kind of big application domain for BlackBox optimization is in optimizing machine learning models. So for things like hyperparameter tuning. For those of you who are not familiar, when you have a machine learning model, you have to train it. There are often parameters that are not directly learned from the training procedure. So things like learning rate and regularization settings. For things like deep learning, you also have kind of architectural parameters that you can tweak in terms of the shape of the network, the size of it, and so on. For things like random forests, you might have something like the number of trees you use, the maximum tree depth, and so on. These kind of problems induce some kind of black box optimization problem where you're trying to select these hyperparameters in order to come up with the best model, typically measured by predictive accuracy, but potentially other things like serving efficiency, for example, or kind of resource usage. Another application domain is in physical design problems, where you actually might like parameterize a space of designs and actually build something and evaluate it in some way. Or if you are interested in something where you can simulate the objective value, you might kind of build it in simulation and run it and see how good it is. So classically, black box optimization techniques have been used for decades for things like airfoil design, where you parameterize the space of wings for an airplane, and you want to find wing designs that kind of have good lift to weight ratios, for example. Right. And there are many other kind of applications in this space. Yet another application domain is in robotics, where you actually parameterize some control policy for a robot, and you want it to essentially achieve some goal, perhaps like walking while kind of making good forward progress, but also using very little energy, or kind of walking very smoothly, minimizing the maximum jerk, kind of physical jerks that it experiences as it's walking. So those are some of the applications. So we decided to develop a service for black box optimization within Google called Vizier. And we kind of had these principally these 5 design goals, right? So it should be easy to use, so people like to use it. It should be available to use, so people would like to use it. You can't use it if it's not running. It should be scalable so that everyone can use it, all at once. Should be able to handle our entire workload within the company. We want it to be highly performant with kind of state-of-the-art search performance with different algorithms. And lastly, we wanted it to be flexible in the sense that we wanted it to be a suitable research platform for black box optimization. And also, we wanted it to allow customizations for kind of advanced use cases, right? Some of these design goals are actually a bit in tension in typical systems. It's often very hard to achieve a system that's both really easy to use and really flexible. It's also often difficult to achieve very high system reliability with a lot of flexibility. So I'll go through each of these in turn. So ease of use, basically the configuration should be absolutely minimal, right? When you want to run an optimization, which we call a study, you just need to specify some kind of name for your study and the parameters that you wish to optimize and a goal of either minimizing or maximizing the objective. And optionally, something like access control lists for like who can read your study, for example. Once you have this, you can actually set up a very simple client workflow. So there are these clients that will be actually running your trials, right? And this can be software or it can be some other process. But for kind of software clients, they will register with a study, say to the system, basically, here I am, I'm going to work on this study. And then they can repeatedly ask for a trial that contains parameters that they should evaluate. They will then run that process, run that trial, whatever that means in the context of the application, and provide back some kind of objective value, right, the results. So we have clients in several languages. We also have a web front end where you can view the results of your study, have various visualizations, and you can actually drive the search directly from the web browser. And for further analysis, we have integration with Collaboratory, which is a tool. It's kind of like Jupyter Notebooks or IPython Notebooks, if you're familiar with those. So we really wanted to build a system that would scale to a very large workload. There's actually a lot of machine learning that's done within Alphabet, and we wanted to make sure that we could handle like all of it, for example. So in terms of scalability, the targets that we were aiming for were kind of thousands of parallel evaluations per study. So Vizier can actually suggest multiple trials to run in parallel. You don't have to run them one at a time. We wanted to be able to scale to studies with potentially millions of trials. Most of these studies will have much stricter budgets, but there are some applications where it actually makes sense to be able to handle millions of trials. And we wanted to basically scale to unlimited studies. Right. And the way we did this was with a distributed implementation. I've kind of drawn a very simplified version of it here, but the idea is you have a bunch of these evaluation workers that are responsible for evaluating your trials. And they talk to a replicated kind of Vizier API. For some of the operations they ask for, it can just talk directly to a persistent database to get the answers or to make the updates. So for example, if it wants to report the results of a trial. One operation that's particularly expensive computationally is kind of generating new trials to run next. Right? And because these trials are expensive, by assumption, we're willing to spend a fair amount of computation to decide what to do next. So in the case that a evaluation worker wants a new trial to run, the Vizier API jobs will actually forward a request to a suggestion service. That suggestion service is backed by multiple suggestion workers. Right? It also creates a token in the database which represents a request to generate a trial. Okay, so-called long-running operation. And then the suggestion worker that picks up that suggestion task basically gets a distributed lock on it and starts working on it, right? And keeps maintaining that lock. And in this way, we can actually partition the work among multiple tasks in multiple data centers and kind of scale more or less indefinitely. So we wanted the system to be reliable because if it's down, people aren't going to be using it. So we followed all the kind of the standard software engineering practices, for testing, monitoring, alerting, release processes, and so on. That's kind of standard software engineering practice. One thing I did want to draw attention to that I think is kind of interesting about this system is that we store the request to generate new trials on the database itself. And if you attach some additional metadata to those tokens, it actually enables the system to perform a bit of introspection on itself. So for example, the suggestion workers are implementing these sophisticated algorithms for generating new trials. And try as we might to avoid it, they might crash due to some bug at some point, right? So when this happens, they'll fail to renew the lock on the distributed lease on this work, and some other aspect of the system will kind of pick it up and send it to be executed by some other suggestion worker. If we detect that this has happened a sufficient number of times, we can basically presume that there's something about this particular study which is causing our suggestion workers to crash, and we can disable it kind of automatically. So this kind of limits the damage that any particular study can do to the system, and it prevents a number of sort of cascading failures. Right. So this kind of introspection is actually very useful for a robust system. All right, so we wanted the system to be highly performant with state-of-the-art algorithms. The suggestion workers themselves are modular. It's very easy to implement and plug in new algorithms. And we've tried out a whole bunch of different algorithms and do research to try to improve whichever ones seem to work best in various ways. So for example, we play with the Gaussian process bandits and sequential model-based algorithm configuration, covariate matrix adaptation, evolutionary strategy, simulated annealing, genetic algorithms, random search and grid search are of course supported, and many other kind of experimental search algorithms. And you might ask, okay, well, which of these is best? So we do a bunch of benchmarking. I should say benchmarking is particularly difficult for black box optimization because it's an adaptive process, and by assumption, evaluating your experiments is expensive, so benchmarking will be extremely expensive. So in practice, different communities work on black box optimization, they approach it differently, but kind of a natural thing to do is to try to come up with benchmark functions that are cheap to evaluate, they're kind of analytic, but they hopefully have some of the complexities of real world data. Okay, so there are actually academic competitions for black box optimization, and people construct challenge functions for those. So we basically looked at one of these competitions and took a bunch of those functions and implemented them, and we kind of used those for benchmarking. Okay, now, as I mentioned, there's really no perfect set of benchmarks because the benchmarks you have should encode the right kind of search biases or induce the right search biases, ideally, and that will depend on your particular application domain, like the problem you're working on. But these are specifically designed for the task, and we think that they're pretty good. We didn't invent these. I've plotted kind of two-dimensional versions of these 8. They all have higher dimensional versions as well, right? So these challenge functions are parameterized by dimension, so there are different versions of them. Right. You can see that there's a lot of diversity here. We have kind of a convex function that has low condition number, the sphere. We have a convex problem that's ill conditioned, the ellipsoidal algorithm. There are algorithms that have varying amounts of local minima, varying amounts of kind of variation. There's one like this Rosenbach function in the lower left is kind of fun. It has contour plots that look kind of like bananas, and it's very difficult for algorithms like gradient descent to work around those contours. So to actually aggregate these, we use a benchmark where we compare it against random search. So random search just uniformly at random picks a new point. And then with these analytic functions, because we know what they are, we know what the exact global optimum is, and we can look at something called the optimality gap, which is how far away from optimum you actually are. And then we can compare the optimality gap of a particular algorithm after T trials to the optimality gap of random search. Okay, so that's what these are plotting in ratios. So this solid blue line is just random search. The red one is something called 2x random search, which is random search sped up by a factor of 2. It gets to pick 2 trials for every 1 trial the other algorithms get. Some authors have claimed that this algorithm in red is really hard to beat, but that was not our experience in the data. And then some other algorithms like GP Bandit in black, SMAC in purple, CMAES in green, and kind of a probabilistic search algorithm that we developed in-house in blue for kind of larger studies. And one thing I want to bring to your attention here is that in plotting this in 4 dimensions and 32 dimensions, there isn't one algorithm that's best for all cases. It kind of depends on the nature of the study. And one thing about Vizier is that it dynamically selects what algorithm to use for your problem for you. You don't really need to worry about it. Okay, so we wanted Vizier to also serve as a research platform, and we really do this with two capabilities. Vizier has an API method that lets a user inject trial values to say, you know what, don't listen to what the fancy search algorithms say, I want you to try this point, right? And users can inject their own trials into any kind of searches whenever they want, but we can also use this capability to allow an external binary to do this. And the external binary basically can pull the Vizier service and say, do the workers need any trials? And maybe it finds out, yes, the workers need 7 trials, right? And then it'll take all the data from all the past trials, feed it to some policy that you've written, and say, okay, here's all the data, generate 7 new trials, go. And you can, say, implement this policy in Python. It's really simple. And then this allows you to experiment with kind of arbitrary black box optimization methods. We've turned the suggestion workers off for your study, so Vizier will never suggest anything by itself. Your algorithm makes all the trial suggestions. And so this allows you to rapidly kind of innovate on the search algorithms while still taking advantage of all of the workflow management infrastructure, the dashboard, and other tools that we have available that are sort of productionized. The second aspect of this is that the trials have parameters, but we also allow them to be extensible. So you can sort of add arbitrary data to these trials. And if you have evaluation workers that know how to interpret this data, so for example, if you have a custom policy that generates trials that don't have any parameters, but just sticks some string in the trial, and then the evaluation workers read that string and they know how to interpret it as some kind of experiment to run, then they can do that and pass the results back and forth. So you're not constrained at all by kind of the format of like some fixed set of parameters. All right, so we built this system, and then we wanted to kind of get word out within the company that it exists and works really well, and we wanted to figure out some kind of cool thing to do. And there are lots of interesting applications for this stuff, like NASA used it to design antennas for like space telescopes, and I mentioned the wings and stuff. But one thing that we wanted to do was try to design chocolate chip cookies, right? So you can parameterize the space of chocolate chip cookie recipes, like the amount of butter, amount of brown sugar and white sugar, type of chocolate chip, how much chocolate, and so on. And then Vizier can generate these suggested recipes, and you can bake them and have humans taste test them and feed back the ratings and iterate, try to find the best chocolate chip cookie, right? So it turns out that even with very simple ingredients, you can get very diverse cookies. So this was kind of fun. And because we didn't really give any prior knowledge to the system, we got some pretty bad cookies. Like these, they look totally raw, but they're completely baked. They just didn't taste very good. This is what happens when you have way too little butter, apparently. So, but science requires sacrifices, and the results were totally worth it. I can't announce them right now, but it's coming, right? We'll announce a good recipe. So one thing is this helped get the word out. It was also really a good test for the system because it forced us to deal with things like noisy evaluation, infeasible trials, right? Some dough was just too crumbly to bake, configuration changes mid-study where we added ingredients on the fly, manual overrides in trials, like we told the humans to bake something and then we didn't do it right. Transfer learning where we adjusted for bake sites. So we started this thing in a teaching kitchen in Google Pittsburgh. And then once we had enough data, we actually moved it over to the full dessert making capabilities of the Google Plex in Mountain View, where they bake desserts for like tens of thousands of employees. And also a good test of developer baking skill and palate. You can actually use Vizier right now to tune your TensorFlow models on Google Cloud Machine Learning Engine. So I encourage you to go check it out. And yeah, that's it. Thank you. Any questions?